In this mini lecture, we are going to derive the last lateral directional stability derivative, which is CYV, the side force due to side slip. The side force during a side slip is contributed by two components. One is a fin contribution, the other is a wing contribution. Now first look at the fin contribution. And the aircraft scenario is the aircraft is in a positive side slip. And now the question I would like to ask is, what's the definition of positive side slip? I give you a few seconds to remind yourself. Okay, so the first, the positive side slip is defined when the wind is from the right of the aircraft nose. So in this case, and we can see the vector V from the right side of the aircraft nose is in positive side slip. Okay, and we can do the velocity decomposition, and especially we're looking at the small v because it's relative to the side force. Okay, and also we can find the side slip angle beta. And since we're looking at the fin contribution, we need to translate this velocity triangle onto the fin. Okay, so it's translated, and we can see this side slip angle is actually a small angle of attack for the fin, and then under this angle of attack, a side force pointing towards the left side is produced on the fin. Okay, so now let's do the derivation. Okay, so first of all, the angle of attack or the side slip angle beta is small v divided by big V, and why is that? Again, it's a small angle assumption. Originally, it's sine beta equals small v divided by big V, and because beta is small angle, we assume, and then we can just apply this small angle assumption. And a reminder for all of you, beta in this case is the unit is in radian instead of degree. Okay, so this is a usual mistake people make. Okay, and then we can calculate the side force, which is minus AF times beta and times half rho v squared times SF. And what is AF? AF is the lift coefficient curve slope for the fin aerofoil, and beta is the angle of attack or side slip angle, and then half rho v squared times SF is a denominator for lift coefficient, and SF is a fin area. Okay, and then we just write it in Y because usually we use Y to denote the side force. And the question is, probably you notice there's a negative sign in Y. Why you get negative sign? Give you a few seconds. And because the reason is why we get negative sign is because the LF is pointing towards the left. It's towards a negative direction. That's why we get negative sign. And then we do the derivative YV, and then the small v can be eliminated. And then eventually we can find the denominator to get the CYV non-dimensional form. And so we can have minus AF times SF divided by S. Now we need to consider the fuselage contribution to the side force. And so it's the same scenario, and this same aircraft are under positive side slip. And now let's consider why the fuselage will generate a side force during the side slip. And apparently for passenger aircraft, the fuselage can be considered as a cylinder. Is that right? And if it's on a positive side slip, as we did before, the total velocity v can be decomposed into a lateral component, small v, and now we can simplify this problem. Okay, so we can replace this problem by looking at a cylinder at a cross flow, finite length cylinder at a cross flow. So that cylinder will produce side force. So let's see the problem. Okay, so the side force from the fuselage is mainly from the drag D of the fuselage. Can you see this problem? And in order to understand it better, and if we cut the fuselage and get cross section, and we can treat this scenario as a finite length cylinder in a flow. So we have the cross-sectional cylinder, and it's in a flow, cross flow from right towards the left, and there is a wake in the cylinder, and in this case there will be a drag produced on the cylinder, and that is equivalent to the side force Y. So this is how a fuselage can contribute to the drag force. And actually this problem, simplified problem I've displayed here, a cylinder in a cross flow, is quite a classical aerodynamic problem. And if we change the Reynolds number, for example, increase the velocity, cross flow velocity, the flow pattern in the wake will be different. Okay, but in the Reynolds number in aviation is quite big, so we can estimate the drag coefficient of being CD equals 0.3, and then the side force, essentially the drag of the finite length cylinder, can be minus 0.3 times half rho v square, small v square, times fuselage area. Okay, so that's the cross-sectional area of the fuselage, and then we can do a bit analysis. We notice this small v is far smaller than a big V, and then we can assume the fuselage contribution to the side force is usually negligible. Okay, so we finish the fuselage contribution analysis. Then in total, the fin and the fuselage contributing to the side force in total can be, for small aircraft, it's in the magnitude of minus 0.3, but for larger aircraft, apparently it should be larger, so it's in the magnitude of minus 0.9. Okay, so until now, we finished all the analysis or derivation of the lateral directional stability derivatives. In the next couple of lectures, we'll continue with the longitudinal derivatives.